So one of the more common ways that we talk about planar kinematics is in our general plane motion is through a relative analysis. And so if we remember that general plane motion, what we're talking about is something that is translating and rotating at the same time. So as it's moving through the plane, it's rotating about some axis as it's passing through, and also moving at the same time, right? Translation and rotation. So when we look at this from a relative analysis perspective, really what we're doing is we're saying, okay, originally we had some rigid body. And so I'm just going to use some general like little pen shape or something to kind of give you a reference of what we're talking about here. But essentially in our normal XY axis, let's say we've got some rigid body. Right? And I'm going to call this A, and I'm going to call this end B, just to give us some reference points to work off of for this shape. So with our relative motion analysis, we've looked at relative motion before, right? We've looked at it a little bit in our kinematics of a particle. Looked at kind of how relative motion works, which is essentially like creating a new frame of reference. So that's the first thing that we're going to do here. We're going to say, all right, now instead of our frame of reference being this, standard fixed XY axis or wherever it is, we're going to say that this XY axis is translating with it. It's moving with it. Where our origin is going to be wherever our reference A is. Like treating point A, treating one end of the body as this kind of fixed reference, even though it's moving, point A is moving, it's this translating reference that's moving around that we can use to base the rest of the entire body off of. So for example, we have AB that's just sitting there in space, and then maybe our AB translates and moves over to, let's say, here, right? It goes through this general plane motion where A has moved and B has moved, and not only have they translated, so that not only have they moved together in the XY plane, but they've also rotated. Right, B has rotated out a little bit, where now it's kind of facing in a different direction instead of being exactly parallel to what it was before. And so what we're doing with this relative analysis is that we're still sticking wherever we have A. We're going to use this as like our base reference point wherever it's translating to, keeping that as a base point so that we can analyze how B is moving relative to that, so that we can calculate our velocity, our angular velocities, angular accelerations, all of these things. In this video, we're mostly going to focus just on velocity here. We're going to talk a little bit about the translation, the position, the displacement parts of it. But really, we're just going to focus on velocity in this video and then build to acceleration in another video. So essentially what we have here is we're treating A kind of like a fixed reference relative to B. And we've got this kind of moving, translating frame of reference that we're working with where the base point is A. So originally, we had from our fixed origin, we had a position vector from the origin to A, and we had a position vector from the origin to B. Right? And then this vector between them, do it in red, this vector along the line of our rigid body here, this is the position of B with respect to A. So it kind of puts in perspective where B is with respect to A, right? That's all it's doing. It's just telling you where B is from A. And this is just our general plane motion. This relationship that we have when this bar is only translating is the exact same relative motion relationship we had in our particle kinematics. So this is going to look a little bit familiar. Our position vector B is going to be our position vector of A plus the position of B with respect to A. Right, just making that triangle with those vectors, just that simple vector addition we had done way back in our particle kinematics. What we're doing here is we've got to account for that rotation as well. So when it's going through this displacement, right, as it's changing, as it's moving from our original point, we've got this displacement, right? A is moved from its original location by dRA, right? This displacement, what's the delta in A? How is the position of A moved relative to its original position? Right, so how is this moved relative to its initial position? We've got delta RA, and that's actually the exact same for top and bottom here. Both A and B move through this delta RA. This is our like translation portion that this is moving through, is this delta RA. So delta RA, this vector, represents our movement, or I guess I should say our displacement due to translation. So that's displacement due to translation. Just from the bar moving, right? Parallel where it originally was. So you kind of get, if I drew like a little intermediate step, we'd have here is AB. And then it's also going through that rotation. So that rotation that we're seeing is that movement of B, right? So that movement of B, if I go from the old B to the new B, that's the displacement, delta RB. Delta RB is where B is moving, and this difference between those 2 points. We look here, this right here, this vector that connects these two vectors here is going to be our displacement of B with respect to A. Right, that's that little bit that moves it, and it moves it through this rotation, this angle theta. Right, so you've got this displacement, dRA, displacement RA due to translation. Then from the rotation, I've got the change in R with respect, the change in position R of B with respect to A. And that's going to equal my displacement RB. Right, the position vector RB, how RB is changing, where the change in RB is due to translation and rotation. So it's capturing both. The movement of B captures both the translation and rotation. Man, I can't spell today. I don't know what that is. Whereas this little change in R of B with respect to A, right, the change, the rotational movement, because originally our RB with respect to A, even though that length doesn't change, the actual magnitude of AB isn't changing, the direction is, right, because it's moving through that rotation. So really, it's representing the rotation, just the rotational aspect of the movement. So that's kind of what we're doing in this relative analysis, looking at our velocity, is that we're looking at the translation of point A, and then also, separately, to combine together, we're looking at the rotation. So it is both the translation aspect and the rotation aspect that we're essentially kind of looking at separately to bring together to give us the overall, that general plane motion. And we can see actually with these displacements, if we go ahead and take derivatives of these with respect to time, so that we have drb dt, equals dRA dt plus drB with respect to A over dt. We're going to get something pretty familiar, right? Take those derivatives of positions, we're going to get velocity. So this gives us a velocity relationship where we're now looking at velocity of B is going to be the velocity of A plus the velocity of B with respect to A. And one really important thing for us to point out here is this guy on the end, this relationship of this drB with respect to A, how that rotational movement is changing. Because as we said we're going through this angle of rotation. So really this d of rB with respect to A can be rewritten as our vector rB with respect to A as it goes through this change of d theta dt, which is going to give us omega. This is what gives us our angular relationship here. Omega times rB with respect to A. Right, and that's just the vector of the bar itself. So not only can we use this relationship as we have it here, but we can also rewrite this so that we have VB equals VA plus omega cross product with RB with respect to A. This is the most common form you see it in. You typically see it as a cross product instead of just the general multiplication. Like you'll usually see it in both vector and scalar form, but in vector form here, we're going to have our omega cross product with B with respect to A. And so this is the equation we'll primarily be using when we're analyzing this stuff. Right, so when we're looking at this general plane motion, the general plane motion is represented by VB, general plane motion, where the translation aspect is coming from our VA, and our VB with respect to A is representing the rotation about A. So it's just the combination of that translation and rotational components that kind of give us this equation, kind of an altered form of how we saw this in our particle kinematics, because we have this whole body to deal with. So what we're looking at here is we've got our absolute velocity of B. So this is whatever velocity B is moving with in vector form. Absolute velocity with respect to the absolute frame of reference, like from the fixed frame of reference, what is the velocity of B? And then what is our absolute velocity of A? I'm gonna make some notes. So our VB and our VA, those are both absolute velocities. Absolute velocities with respect to the frame, right? Are with respect to X and Y, our fixed frame reference. Then we have our omega, and this is the way that the bar appears to be rotating about the Z prime axis. Right, so we have this bar up here, and I'm running out of colors that are going to stand out against each other here. But if we think of A as like where our Z-axis is pointing out of the screen at you, which way is the bar rotating around point A? So in this case, it looks like we're swinging around this way. Right, the B is kind of swinging out around point A, going, I guess, in a counterclockwise fashion around A. So this is our omega. It's directional. So omega, that's the way the bar appears to be rotating. So this is relative. appears to be rotating about the z prime axis passing through A. And then finally, you have probably our most self-explanatory one. This is just the position vector. Position vector of our bar from A to B. So again, with all of these things, we're kind of using our A as like this base point that is going through this translation and rotation where everything is kind of referenced off of A instead of being referenced off of the like XY origin, right? Everything's just being referenced off A instead, except for those absolute velocities of A and B that go into this equation here. So before we walk through some examples, let's kind of talk through some steps you want to work through or some things you want to think about as you're analyzing these problems, kind of how to approach it. Because one of the interesting things about it is that you can approach it with the vector form or in a scalar form, and those approaches kind of differ a little bit in how you draw the free body diagrams and kind of how you think about the problem in general. So we'll talk about how you kind of analyze and think about these things, and then we'll work through our examples. So first, and I would say not more common, but honestly usually easier, is vector analysis. Doing it in a vector way instead of doing it with our scalar analysis. And I know some people like have a lot of feelings about vectors, and you know, you're like, oh, what way does it point? But honestly, vectors really save you a lot in your sign convention. Like if you can set up everything with the vector analysis, it's so much easier to get the correct signs on things than when you're doing a scalar analysis, and you can really mess up the signs a lot easier, in my opinion. And maybe you like scalar analysis more, and more power to you. You can use scalar analysis. I really don't care. I'm going to show you both ways. Just know you can do it either way. Scalar analysis tends to be not the default. I default to vector analysis a lot of the time in these problems. But that's just a personal preference, and you can do whatever you want. So when we're doing this in a vector analysis, what we're going to want to do is we're going to want to establish our x and y direction, right, as we do when we start pretty much all of our problems. But really the more important thing is drawing that kinematic diagram. So draw a kinematic diagram, kind of like a free body diagram, but not forces. You're just going to put your velocities on there. Right, so you want to put VA, VB, and you want to make sure you're giving them the correct direction. Really, that's going to be the biggest key, is making sure that you are giving those correct directions so you can refer to and set up all of your signs correctly. So VA, VB, omega, and the position vector of R of B with respect to A. Putting all of those on your kinematic diagram with their correct directions, or in some cases assume directions if you're not 100% sure what the direction is. Like angular velocities, sometimes it can be a little bit difficult to know which way it's rotating through the motion. So you may have to assume a direction, and if you get the opposite, like if you get a negative value, then you know that you've assumed the wrong direction for our omega, for example. But generally, like with our regular velocities and our position vector, we definitely want to make sure we have the right directions on those. Then what we're going to do is we're going to express all of our vectors in Cartesian form. So that's your IJK format, if you remember. Vectors in Cartesian form. That's I hat, J hat, K hat, that kind of form. And although we kind of brushed over this as we were discussing it when we said our omega is usually clockwise or counterclockwise. And so what that means is that it's going around, if we use our right hand rule, our thumb is going to point in the direction of whether it's in the positive or negative direction. So for example, when I curl my hand, as I have it on the screen there, when I curl my hand in the counterclockwise direction, my thumb points out of the page. It points directly at me. And this is the positive z direction. Like coming out of the page is the positive z direction, and going into the page is your negative z direction, since your xy is the screen, right? So out of the page, this would be a positive k hat direction, right, as it's rotating around this axis here. If we came around this way, this would be our negative k hat direction, right? Because when I do my thumb points into the screen. When I curl my fingers around in the direction of that twist, right, of that clockwise motion. So our omega, our angular velocity, is always going to be some kind of k hat. It's just a matter of whether it's a positive or a negative. All right, so we drew out our things, we wrote them in Cartesian form, and now what we're going to do is we're going to separate all of the I components and all of the j components. So we're going to have one formula that is just all of the I components and one formula that's all of the j components. So we're going to equate all I hat and j hat components, right? These are like your x and y components, into two equations to solve for unknowns. Right, so essentially it's like if you have, 20 I hat equals 7 I hat plus 27 omega, just for example, j hat, that's a terrible example. I don't know, minus 3 j hat plus VA I hat. This is such a horrible example. But what you would do is you would take all of the i's and you would make these into an equation. So you'd say 20 equals 7 plus VA, and then you'd take all the j terms and you would say 0 equals 27 minus 3. Right? So you're just separating out into two different equations the I hat and the j hat components. And then you've got two equations. Generally, you have two unknowns. If you've got one unknown, you really only need one equation to set up. But you're separating them out into those I and j components, so you've got two equations and you can solve for two unknowns. So in these problems, you're typically given two of these four variables, and then you have to find the other two. Sometimes you only have to find one, but generally this is often what these problems are asking for. So, as we mentioned, not only can you do this with a vector analysis, but you can also do this with scalar analysis. And really the difference is in that kinematic diagram, in that initial setup. So if you want to do this in scalar analysis, what we're going to do is we're still going to start with drawing that kinematic diagram. A kinematic diagram. But now what we're finding is just a little bit different. Now what we're establishing, in addition to our VA and VB, is instead of omega and our position vector, we're going to be finding the vector of velocity of B with respect to A. And that velocity of B with respect to A, or some bar here, let's say they gave us this angular velocity or something and it's rotating this way. Here's A, here's B. Our position vector that goes through this is going to be our R, B with respect to A. And our velocity vector is always going to be perpendicular to that, in the direction that it's swinging. So that means that our velocity of B with respect to A perfectly perpendicular, B with respect to A, in the direction of omega, right? In the direction that it's swinging around A. So we have to draw this kinematic diagram just a little bit differently. We didn't have to account for this B with respect to A because we had split it up into omega and RB with respect to A. But for scalar analysis, we absolutely need this. We need the direction of this VB with respect to A, and that is given by our position vector of B with respect to A because it's perpendicular to that. Right, so RB with respect to A, you go perpendicular from that, that's how you get the vector, the direction of vector B with respect to A. I guess we could say, so VB, let me write this a little bit better. We're going to need our B with respect to A, or velocity, B with respect to A, where you're going to get the magnitude of this comes from omega times RB with respect to A, like just the values of omega times RB with respect to A, and the direction is perpendicular to R of B with respect to A. So once you have all of that in your kinematic diagram, you're again going to break up your vectors into your, instead of into your Cartesian form this time, you're going to break them up into x and y components. So break up vectors into x and y components. And then your last step is going to be using this VB equals VA plus VB with respect to A for x and y equations. So you're going to do that equation twice, once for x components, once for y components. Equations separately to solve for unknowns. So they're very similar, right? You're still essentially, in either case, you're separating out the x's and y's, right? Like in your vector form, you're doing i's and j's, which again, they're just your x and y components. And in your scalar analysis, you're also separating out x's and y's and using an x equation and a y equation. So again, two equations, likely two unknowns, maybe one unknown, two equations that you can use to solve for any unknowns in your problem. The major difference, again, is that kinematic diagram and what you're actually using to solve the problem there. So in our first example, I'll walk through it both ways. We'll do our first example in both a vector analysis and this scalar analysis, so you can kind of see how each of them work. And then we'll do a few more examples after that, so you can kind of get a feeling of these general plane motion problems. Let's take a look at this first example together. So we've got this link that's shown that's guided by blocks A and B, which move in the fixed slots. If the velocity of A is 2 meters per second downward, determine the velocity of B at the instant when theta is 45 degrees. Right, so we've got, I'll kind of draw like a free body diagram for this guy, our kinematic diagram, what we always want to start with. And I think I'll start with vector analysis. We'll go ahead and do both vector and scalar analysis for this, so you can kind of see how both work. But we'll start with vector. So approaching this problem with vector analysis, let's start with my kinematic diagram where we have this bar AB. Got point A over here, and then point B, this time not quite at the end of the bar as we've kind of been talking about, but he's just another point on the bar there. And the things that we want to draw are, we want to draw the velocity of A, the velocity of B, our direction of our angular velocity omega, and then finally that position vector of our b with respect to a. I'm going to draw each one of those guys in here. So VA is our most obvious one to start with. He's indicated on the diagram over here that our velocity of A is just straight down, right? He's stuck in that groove slot. There's really nowhere for the velocity to go except for either up or down for point A, right? We're not looking at the full body, just point A. Where is point A moving? And in this case, our point A is moving directly downwards by 2 meters per second. So if I wanted to put that into Cartesian form, that downwards is the negative y direction. So actually I should put a negative in there. Negative 2j hat. That's our velocity vector there at A. Then I'm going to come over and I'm going to look at my point B. So B, we don't actually know. Like, we don't know B. We're trying to find B. So we're going to have to make an assumption on how this thing is moving. And so since A is moving down through the slotted groove, we can also kind of see the ghost of it as it's traveling in this image here. But as A is moving down, really the only direction for B to move is to the right. Right? It can move either left or right because it's in that fixed slot. But because A is moving down, it's going to force point B to move to the right. Draw that a little bit straighter. There we go. So our velocity of B, we don't know the magnitude, but we do know that it's in that positive x direction. So our VB is going to be VB I hat. Right? It's something in the positive x direction. It has no y component to it. Just x, just that I hat there. So we have VB, we have VA. I guess you can write it VB equals VB I hat. VB, VA. Next, let's kind of talk about the rotation that's happening. Right? So we've got kind of a rotation around point A, right? The rotation of B from the perspective of point A. So what that looks like is that I'm trying to think of what way B is kind of moving with respect to A, and my only options are that the bar is moving in a clockwise or a counterclockwise fashion. Right? Those are my only options. And looking at the way the velocity is going, it looks more like I've got this counterclockwise kind of omega. Right? This way B is kind of pushing out this way underneath A. B is pushing out, right? Kind of like a moment about point A there, that B is moving to the right, so that omega is kind of in a counterclockwise. We'll assume it's a counterclockwise around point A. And then finally, the last one we need that position vector of R B with respect to A. So that's our position vector from B to A. And so if we create this position vector, B with respect to A, what we're going to see is this is where our 45 degrees comes into play. Right? We have an overall length here of 0.2 meters. And so our position vector, remember, we're just going to get our x component and y component of that. So if I do 0.2 times sine 45, that's going to give me my x component here, right? X component of this vector, and then my y component of this vector is going to be 0.2 times cosine 45. So I have 0.2 sine 45 I hat, and that's in the positive x direction. And then my j hat, my y, it's in the negative y direction. 0.2 cosine 45 j hat. So that's my full position vector for this guy. All right, so we've written out all of our components. We've defined them in their Cartesian forms. So now let's start kind of putting some things together. Okay, so we've got our general formula is VB equals VA plus omega cross RB with respect to A. So now I'm going to put in all this stuff that's in Cartesian form. I'm going to plug all of this into our equation. So VB, I know, is VB I hat. Then VA, I know, is negative 2 J hat. Then omega, remember our omega is always going to be in the K hat direction in these problems. So in this case, it's rotating in a counterclockwise fashion, which is positive K hat. So that's going to be plus omega. We don't actually know what omega is. We don't know what the angular velocity is here. We'll just leave it as omega for now. Omega K hat cross product with our position vector there. 0.2 sine 45 I hat minus 0.2 cosine 45 J hat. And so I'll go ahead and do this cross product. So we have I, J, K, and then we have 0, 0, omega. Then our bottom line there is 0.2, I guess I could simplify that, 0.2 sine 45, that's 0.141. 0.141 for both of those. 0.141, and then a negative 0.141, and then a 0. So we're evaluating that cross product, and what we end up with is 0 minus omega times negative 1.41, so that's 0.141 omega I hat. And then we do our J hat terms, so that's another 0, and then minus negative 0.141 omega J hat, and then our K hat terms both go to 0. So if I write this out, I'm going to get VB I hat equals negative 2 J hat plus 0.141 omega I hat plus 0.141 omega J hat. Now there is actually kind of a quicker way you can do it if you don't like writing out this whole big cross product thing. We know what the cross products of unit vectors are. Like, these are general known things. Anytime you're taking the cross product of an I hat cross a J hat, you're gonna get K hat, right? If you're taking J cross K, you're gonna get I hat. So for our cases, what's gonna be really useful for us, since we're always gonna have a K hat crossed with either an I or a J, I'm gonna put these, I'll put this in light purple here. So when we have K hat cross I hat, that is always gonna give you a positive J hat. And when you have K hat cross J, that's gonna give you a negative I. Right, so be cognizant of the signs, but we're always going to have, because of omega always being a K, it's always going to be a K cross an I and then a K cross a J. And then you can just multiply their front numbers. Right? So omega times 1.41, and then the K cross I gives you J hat. And so that's how we ended up with this term. So the other one we had K cross J, and it was originally a negative number. And so that's how we ended up with a positive number here on our I hat. The two negatives canceled out. Or the two negatives became a positive, I should say. So just know you can use these guys as a handy little shortcut if you don't like doing the long form of cross product every time. The long form of cross product, I guess, could help you on your signs a little bit, but it's up to you. I'm just showing you more ways you can do stuff. Anyway, now we can finally get to the point where we're actually going to do something. So now that we've done all of this, we have everything in terms of I hats and j hats. And this is how it should always work out for you in these general plane motion problems. It's only two directions, right? We're not moving into 3D here. You shouldn't end up with any k hats. You should only end up with I hats and j hats. So with your i's and j's, what you're going to do is you're going to set these up so that you have all of your I hat ones in one equation and all of your j hats in another, right? Think about just separating your x values and y values. That's all we're doing here. If I take all my I values and equate them, I get VB equals 0.141 omega. And then if I do my j hat, there's nothing on the other side, but there is a -2 here. -2 plus 0.141 omega. So see, two equations, two unknowns. We can very easily solve this j hat one. We can solve this for omega. So if I rearrange and plug it into the calculator, I get omega is 14.1 radians per second. And then I can take that and plug that in right here to find my velocity of B is 1.41 times 14.1. I got 2 meters per second, right around 2 meters per second. This is what we were looking for, right? We were looking for that velocity of B. And if you want, you can go ahead, you can slap a j hat on it, or an I hat on it for direction. You can give it a directional arrow. But really, we can just give the magnitude. It didn't specify. So velocity of B is 2 meters per second in our I direction there. So that's the process with this in this vector analysis. Right, you're going to write out all your components, put them into your equation in the Cartesian form there, then separate out your i's and your j's, and you should be able to solve for what you're looking for, whether that's your velocity or angular velocity. Any of those velocities you should be able to solve for. But let's do this problem again, looking at it through the lens of a scalar analysis. So I'm going to go ahead. Do I want to keep all that up there? I think I do. I'm going to get rid of this cross product over here, though. And I'm going to move this too. I'm going to draw my picture over here so we can kind of compare the two pictures. So let's move that over there a little bit. And then get rid of these guys. Sorry, I don't know why I'm working through this out loud. I'm just letting you know my thought process, I guess. But we're going to do the scalar form. So scalar analysis. Scalar analysis here. And so again, the key with this is that we draw and think about our kinematic diagram just a little bit differently. Because instead of working with these vectors and this cross product, what we're working with is x components and y components for VB equals VA plus VB with respect to A. So it's that B with respect to A, this guy at the end. He's the one who causes some problems. He's the one who gets treated a little bit differently when we draw our kinematic diagram. So when we draw this kinematic diagram, what we're going to see is that we have still the same VA and VB. So still the same, here's your bar, here's A, here's B. Our VA is still -2. It's still in that negative y direction. So VA is still 2. B is still moving in that positive x direction. Of course, this position vector, our b with respect to a, that of course is going to be the exact same, right? Nothing has changed there. The difference is the addition of that vb with respect to a. And so that vb with respect to a acts perpendicular to our rb with respect to a. So this guy vb with respect to a. And this angle here, I'll go ahead and note that in, that is 45 degrees. Right, this AB is at a 45 degree angle, so when we're perpendicular, it's still at a 45 degree angle. So with this scalar analysis, we're breaking this up, every vector we see here, into x and y components and plugging in to this equation here. So I think I'm actually going to get rid of all of this stuff we had before. And we'll start fresh, writing out our VB equals VA plus VBA. All right, so our x components, we look at all of our x components here. The x components, VB, does VB have an x component? Yes, VB is entirely x component. So we have VB equals, does VA have any x components? Say, nope, VA is entirely in the y direction, so there's no x components for VA. And then we look at VB with respect to A. VB with respect to A, again, this new vector that we've had to create here, that is going to have a magnitude, right? The magnitude of VB with respect to A is omega times r. So omega times r, and that r is 0.2. Right? That r is just 0.2. It has no direction associated with it. We get the direction from this angle from VBA. So that's going to be plus, because our VB with respect to A is in the positive x direction, 0.2 times omega, that's the magnitude, and then to get the x component of it, that's times sine 45. Or I guess it's cosine 45 in this case. The way I drew that angle on here. Cosine 45, since it is adjacent. And that's all of our x components. So now we'll go and do all of our y components. So VB has no y components, that's 0. And then we'll have VA. Does VA have any? Yes, it has 2 in the negative y direction, so that's a -2. And then VB with respect to A is again in the positive y direction, has a magnitude of 0.2 times omega, and then the y component portion is sine 45. So from there, now it's the same process again of you've got 2 equations, 2 unknowns, you're just going to solve them. So I'm going to use my y equation. With that, I can solve for omega, and again, I get the exact same 14.1 radians per second, which I can then plug in here, solve for VB, and we still get that VB is 2 meters per second. So 2 different ways you can solve it, 2 different ways you can kind of think about it if you like a vector or if you like a scalar analysis more. Again, I feel like sometimes it's easy to mess up the signs on the scalar analysis. So the vector analysis, I feel like, is a little easier to tally and kind of keep track of as you're working through the problem, especially on more complex problems. But again, it's up to you. You can kind of choose what approach you like, what works for you, what makes sense for you as you're working through these problems. So with this general plane motion, again, it's mostly finding velocity or angular velocity, depending on what the problem's asking for, and then just working through with your kinematic diagram, finding the equations you need to find those unknowns. Let's do another example where this one is a little bit more complicated because now we've got two bars that are pinned together and their motion is dependent on each other. So in this one we have if bar AB has an angular velocity of 4 radians per second, determine the velocity of slider block C at the instant shown. So really at that pin connection at B there that's connecting bars AB and bars BC, we're going to want to split them up, right? Kind of analyze AB and BC separately, see what's going on with each of them and how they're impacting each other. So to find that velocity of C, and I'm going to do this one entirely in vector analysis. To find this velocity of C, if I look at this bar BC, I can see that C is trapped. C is moving on this fixed track there, that it can only move either to the left or to the right. And looking at this way that bar AB is kind of rotating, I'm not sure, maybe it's moving to the right, it could be moving to the left, maybe I'm not sure. Maybe it would be better actually if I start at what I have known, right? That angular velocity of AB is 4 radians per second. So instead of trying to force my way working through this CB, even though I want to find that velocity of C, I'm actually going to come over and start with bar AB. I got A at the bottom, B at the top there. And when I look at just bar AB, I'm going to notice that I have this angular velocity they gave me, 4 radians per second. But I also notice that point A isn't moving, right? There's no velocity of point A. It's fixed in this pin. There's no way for there to be a velocity of A. So really, since AB is just rotating about that fixed point A, I can go back to that last section we had done where we did rotation about a fixed axis. Right? I don't actually have to do any big complicated vector analysis with this one. Since it's just rotating about this fixed point, I know that my velocity of B is just going to be the angular velocity times RAB, right? That position vector. So, and just the scalar of that, right? Where VB is going to be perpendicular to this vector RAB, right? R of B with respect to A. So my VB here, when I go to calculate it, I'm going to get my VB is this bar has a length of 150 millimeters, and I've got that omega of 4, so 4 times 150 is going to give me 600 millimeters. I just realized I didn't bother to convert out of millimeters, which is fine. It just means my units are going to be in millimeters per second instead of meters per second. And so that's fine. So VB is going to be 600 millimeters per second. And then before I actually move that VB over into my CB diagram, I'm going to break this up into its components. All right, so here I had this angle is 60 degrees, which means if this comes out like this, that this angle would also be 60 degrees, and I know that they're perpendicular to each other, so that means this angle has to be 30 degrees. So I can reconcile this into its Cartesian form. Right, now that I know that this angle relationship, I can say the vector VB is going to be 600, and then it's in the positive x direction, so 600, and the x component here is going to be cosine 30 I hat, and then we're in the negative y direction, so minus 600 sine 30 j hat. So that gives me my vector in Cartesian form. And this vector for VB that I have is going to be the exact same vector that I'm putting on member CB. Right, so still down in that negative 30-degree direction for my vector VB. Go ahead and note that here too, that that's still down in that negative 30 direction. That's the direction that our B is moving. So now I'm going to want some of that other stuff that we had talked about, right? Where I'm going to want VC, of course that's what I'm trying to find, the velocity of C. I'm going to want a representation of how the angular velocity is moving in this bar, because it's different from bar AB. Right? Bar CB is going to have a different kind of angular velocity there. And then I'm also going to have a different position vector. At this time, my position vector from B to C. I have R of C with respect to B. And if I find that vector, I see that I have, oh gosh, I'm going to have to write this somewhere else. So this vector of RC with respect to B, we have this 30-degree angle here from our diagram, and we know that length is 200. So my x component is in the negative x direction for this vector, so negative 200 times the x component of that is sine 30 hat. And then we're in the positive y direction, positive 200 cosine 30 for that y component. All right, so we've got our VB, we've got our position vector of RC with respect to B. Now we'll have our rotation, right? So C is either moving to the left or to the right. We know that VC is going to be entirely in the x direction. I'm going to make an assumption that my C is moving to the right. Okay, kind of based on what I'm seeing, I think that it's going to be moving to the right. I'm not 100% sure, but my signs will all work out in the end. Right? If I get a negative sign, it means my vectors go in the other way. Right? So I'm going to assume it's going this way, which means that my rotation about point B for my omega has to be going like this. Okay, my omega has to move like this around point B to get a VC that goes that way. So my VC is just going to be VC I hat, and then I've got omega, and I don't know what omega is, and I'm just trying to find the velocity of C. So now I'm going to take all of this and put it into our equation. So that equation that we have is now VC, since I'm using C's and B's this time, VC equals VB plus omega cross RC with respect to B. And I'm going to start plugging stuff in. So I've got VC, I know that's VC I hat equals VB 600 cosine 30 I hat minus 600 sine 30 j hat. And then I've got omega, and it looks like omega this time is a negative omega k hat, right? It's in the negative direction because it's going in a clockwise fashion here around B. Right, clockwise around B, that's causing a negative k. We're going to cross product that with our RCB. So R of C with respect to B, negative 200 sine 30 I hat plus 200 cosine 30 j hat. And I'm going to evaluate this cross product. And so since I know that my k cross I is just j, that means I'm going to get omega times 200 sine 30. So omega times 200 sine 30, and I should probably simplify that. That's going to be 100. So a negative times a negative is a positive. 100 omega. And then the I cross k, that gives me a positive j. And then I have omega times 200 cosine 30. And when I plug that in the calculator, that is about 173.2 omega. And then I have k cross j. K cross j gives me a negative I, but because of this negative out here, that's going to make it a positive I hat. Right, so that was just using my shortcut of k cross I and my shortcut of k cross j to evaluate this portion here. And so all the rest of this stays the same. Right, the VC, I guess I could simplify this. 600 cosine 30 would be 520 I hat. And then 600 sine 30 would be 300 j hat. And that's a plus. So I'm going to separate all of this out into just the I hats and the j hats. So I'm going to have for my I hat components, I'm going to have VC equals 520 plus 173.2 omega. And then the j hat components, I've got 0 equals negative 300. The other j I've got is plus 100 omega. So there I can see if I move the 300 over, I get omega is 3 radians per second. And when I plug that in there, I get my velocity of c is a positive 1040 millimeters per second. Again, I didn't convert any units, so I get millimeters per second. If you did convert everything to meters, you would just get 1.04 meters per second. That's a totally acceptable answer too. And we guessed correctly. All of those worked out to be positive values. So it means that we guessed the direction correctly in those initial diagrams, right? In this kinematic diagram up here. So sometimes you have to take a step to get to the values that you're looking for. Like here we had to convert this omega AB from this fixed rotation to get to that general plane motion. So sometimes you've got multi-step problems like this when you've got to account for things in order to actually get to the general plane motion that you're solving for.